Oh, you do?
Yeah, go off today.
You literally have it. Oh, you do? We're on the same
All right, you ready? No. I don't know. You have to look at it. Yeah. Yeah, before you get a big person lab. Yeah, we all went through that one. Okay. So I want you all to be aware that we have a scholarship deadline on campus of March 1st. Okay, so you need to apply. There's nothing more frustrating as a faculty than to open it up and go, 2 people applied, that's it? Okay, when I know there's 50 of you, okay? So like, apply. So we're trying to really push to get you guys. We want to do money. Believe it or not, I know. Shocking, I know. Okay. So this little thing up here should go away. Yeah, it should be recording. The little button's flashing. Does that mean something? I did a practice.
Are you recording?
Yeah, I am trying. See this? The green, that means it's recording. Okay? All right, and I keep thinking this thing is going to go away. This little thing up here. Doesn't it normally go away?
Don't you slide it up or no?
Like that much? I don't remember it being there before.
I think I agreed with Victor last time. Yeah, for being honest.
Yeah, but it's all the same dimensions, isn't it? All right. Well, anyway, this will be posted later. And did you see what I did for the folders? They're by each month. I couldn't add that later and then move them all in. I tried to have one and then have the months in there. The Blackboard would not let me do that. Really weird. I think it was because it was a video. It didn't want me to go too many levels. So I just set up the folders that way from the get-go. All right, so here we have addition of HBr to an alkene. So if we add HBr to this alkene, what do we get? I'm not going to push the button until you tell me. What do we get? What kind of a reaction? Addition, okay. So what are we going to get? A what? One carbon gets a hydrogen and one carbon gets a bromine. Who gets what? What does this one get?
The bromine.
Okay, the bromine, and this one gets the hydrogen. Okay, and I think this is something about Markovnikov. Okay, what if you wanted to go the other way? So there were some people in a lab, and I honestly don't remember who it was, the name of the scientist anymore, which is pretty sad. I should find out. But, and I'm sure the poor graduate student was berated, like horribly by the professor, because they went in and they did the reaction with the HBr that they had, and it added anti-Markovnikov. So what do you think anti-Markovnikov? Opposite, right? It's flipped. So in other words, this guy got the hydrogen and this guy got the bromine. And I'm sure that professor will just beat that poor student up and said, no, you must be doing something wrong. And he kept repeating it. And so they finally went in and looked at the bottle of HBr. The bottle of HBr was contaminated with something called peroxides. Okay, so peroxides have an OO bond in them. Typically, hydrogen peroxide is the one that people have heard of the most because you can buy that at the grocery store, and it's HOOH. Now, don't drink that, right? Okay, a guy went into the bar, he ordered H2O. The barkeeper gave him H2O. The next guy said, I'll have some H2O too. He gave him that and he died. So don't drink H2O2. That's the moral of the story. Okay? But this bond right here, this OO bond, I need a color. This OO bond is really labile. That means it breaks easily. Okay, I haven't used that word. Okay, and so what happens is you get this, the Anti-Markovnikov product. Okay, that looks really light though. I guess it's not so light. Okay, so what is has changed? Well, the mechanism has changed. Okay, when you use peroxides or something with an OO bond in there, we're going to see a couple of other ones this semester. What happens is you change the mechanism. The mechanism that we did for the first part that we did last time, where we went through a carbocation. Here, it's all free radicals. Do you remember those? So the mechanism has totally changed. Okay? Now, a couple things. You're going to have some free radical mechanisms and some regular mechanisms that use 2 electron transfers. Free radical mechanisms always are 1 electron plus 1 electron makes a bond. Remember? I know, you slept since then. I hope you did. Okay? But we don't mix that. We're not going to have free radical and carbocations formed. That ain't going to happen. Okay? It's going to be one or the other. So you have some clues to know which one it is. You know it's free radical if it's got peroxides. Okay? Or the clue that we learned last semester was H nu. Remember that? Okay? That means that we're adding energy to break a bond. Okay? So it's important that you know whether to do free radical or to do the regular 2 electron. The vast majority are the 2 electron transfers. Okay? So you need to hone in on which ones are free radical. Okay? And yes, we're going to do it. Because you got to know why. Okay? Remember that when you do a free radical reaction, there are 3 types of steps. Initiation, propagation, and termination. Okay? We're always going to have those when we do free radical. Okay? Wow, how did I do that? Okay, so in our initiation step, what's going to happen is our free radical is going to first be formed by the peroxide. So 1 electron in the O bond is going to go to 1 and 1's going to go to the other. You still will have some H nu. Sometimes they'll write it and sometimes they don't. So peroxides really is going to be your clue. Sometimes they write a structure like HOOH, okay, like this. Or you'll see it with a pH. Do you remember what pH stood for? It stands for a benzene ring. Okay, so write that down and we'll talk more about why that stands for a benzene ring and not a B, okay, when we get there. But sometimes it'll list the H nu and sometimes it'll just say the word peroxides, okay? If it just says peroxides, just use the hydrogen, what I advise. Okay, so we're breaking that apart and we're making 2 free radicals. Okay, everybody see how we went from there to there? Okay, here's the next one. Now what's going to happen is that free radical is going to react with HBr. Okay, remember, 2 electrons make a bond, 1 electron from the free radical, 1 from the hydrogen. Okay, that's going to give us, what is ROH? What kind of compound? That's an alcohol, right? Okay, plus your bromine free radical. Okay, I just don't have all of those electrons on there. Okay, and now you'll see that initiation actually has 2 steps. Before it always only had 1, like the bromines busted. Okay, now we're using this plus this. It's very hard to bust HBr apart with light, okay, or heat. All right, so we formed our bromine free radical, so now we move to propagation. Maybe. There we go. Here's propagation. So our bromine free radical is going to react with 1 of the electrons in the pi bond. Last time when we added HBr, the pi bond reached out and grabbed a hydrogen. Notice that we're adding the bromine to the molecule first. So what kind of free radical do I form over here? Are you writing all this down? Is that what's going on? Let me get a darker color. This is a secondary free radical. Okay, if the bromine had chosen the carbon over here and the free radical had gone here, that's the other option. It would have been what kind of free radical? Primary. Right? Are you awake yet? Let me have to hand out coffee. Okay, so which is more stable, secondary or primary? Secondary, okay. Okay, here's the next step. Now that secondary free radical that we made will abstract a hydrogen from another molecule of HBr, and look what we made down there. What is this? A bromine free radical. And what does the bromine free radical do? It goes up here and does this step all over again. Okay, your propagation steps are going to make that little chain, that cycle that's going to keep repeating over and over and over. Okay, no matter what the free radical is. Now, why doesn't this just take the bromine and make a hydrogen free radical? Hydrogen free radicals are very high in energy. They're very hard to form. Okay, it's easier for a bromine free radical to form than a hydrogen free radical. The bromine is a bigger molecule. It's got more electron density and protons to help stabilize the free radical. It's a more stable radical, so it always goes this way. You don't ever add a bromine and then have a hydrogen free radical. Okay, so these don't form. Okay, I'll just write don't form, so you'll know why it was there. Okay, what was the third kind of step now? Termination. Okay, let's see if I've got them on. I have to do that. Okay, here's our termination steps. Okay, so we're going to take our free radicals and we're going to put all the combos together. Remember that the vast majority of your product is formed in the propagation steps. These are small formers of products, okay? You don't get a lot of bromine formed. You get a little bit though. And so you're going to do basically all the possibilities. You're going to throw your free radicals together. Now, what about that initiator thing, the hydrogen peroxides, okay? Don't put them in your termination steps. There's just a small percent of that in there. And remember that there's only a small percent of free radical formed at any given time. It's not like the whole thing goes boom and all of the free radicals are formed immediately. It's a process, okay? If you were to run this reaction in lab, it would probably take a little time, like a couple days, okay, is typically how it works. All right, so here is our organic molecule free radical plus the bromine. Okay, so we've got the bromine plus the bromine, the organic molecule plus the bromine. What's the last one? The organic molecule plus the organic molecule. Okay, so remember that you're making the new bond between this carbon and this carbon. Okay, so this is the new bond right here, the one that's purple that I'm coloring green for whatever reason. Okay, a lot of times people just want to make the ends like they want to go from here to here and just make a really long compound. Remember, it's the free radical carbons that are coming together. They're shaking hands, making the bond. Oopsie dokie. So is that too bad? That review a few things. Okay, the big new thing in it really is the hydrogen peroxide, and that you're adding HBr. We added Br2 or Cl2. We're adding something that's unsymmetrical. Okay. All right, so if you look at this top compound up there, we've got that alkene plus HBr and peroxide. Okay, so what is the major organic product for that? What do you think? So what kind of reaction is it? It's what? Addition. And what mechanism is it? Free radical. Okay. What are we doing to the double bond? We're adding a what and a what? A hydrogen and a bromine. Okay. Who gets what? Who gets the hydrogen and who gets the bromine? You mean this one gets a, this one is Anti-Markovnikov. I'm going to write anti-mark. I don't have any student's name on this.
Primary carbon will get the bromine.
Yes, and this carbon over here on the left will get the hydrogen. So we're going to make that. Okay? This is your clue so that you know which one it's going to be. That's your clue. And that's the way in the lab you can make the one you want. So if you wanted this one, you would make sure that there was peroxides in your reaction mixture. Okay? You wouldn't heat it up so much. A bunch of little conditions there. Okay? Note that the carbon skeleton did not. Okay? Only the carbocations. Okay? That's all you got to remember. Carbocations rearrange. Okay. So now, what if we switch it to HCl? Because the people who did HBr said, let's try HCl. We can add HCl to a double bond. Well, guess what happened when they did that? They still got the Markovnikov addition. The anti-Markovnikov with peroxide only works with HBr. That's the only company who uses HBr. You can't use HCl, HI, or HF. Okay, only HBr, hydrogen bromide, will do it. Okay. Okay, now the reason for that, you're just like super interested, is that the propagation steps when you use HBr are exothermic. With the other ones, they're not. They're endothermic. You have to add heat. And so if you add heat, then it flips to the other mechanism. They can't do. So that's the reason. But all I care is that you know that which one it is. Okay, so if somebody puts this in a multiple choice test, don't let that trick you. The effect only works with HBr. Okay, not that I would do anything like that. Would I? Somebody just put Okay, so look at this one at the top. So what are we going to get now? We've got that double bond plus HBr and peroxide. You don't have that one?
It's the next. there's
Oh.
one in between.
I had one in between. What I had in between?
There's a re-
I'm not gonna worry about it. You can just put a little X on, or maybe it'll show up later. Maybe I'm not bored. That has happened. All right. So what do we get? And this carbon is going to get the hydrogen. Okay. Oh, now you see I put a little asterisk there. You remember what that's saying for? Chiral center. Okay, so notice that we made a chiral center. So what do you think? Did we make R? Did we make S? Did we make them both? What's your guess? Both. We made them both. Okay, this one and this one. Okay, free radicals. The carbon is sp2 hybridized, and then you have your little loose electron in the orbital, and so you can come in on either side, for the next part. So it just is to do the hydrogen abstraction. So it's just you get both. You wouldn't get one or the other. Okay, you would get both. So those little things like chirality are going to keep kind of coming up. Okay, throughout the whole rest of it. And I know you like that chapter so well. All right, so did you all draw that or whatever you wanted? You want? I'm not even going to ask you to figure out which ones are and which ones are. We're not even going to worry about that. You know how to do that, right? Sure. Yeah, when we need it, we'll do it. All right, are we good? All right, here we go. So what is the major organic product? Look at here, I have a little seat. Try to put it over here. I don't know, I seem to like to be on this side. Whatever. All right. Everybody's here. All right, so do I have 21? Okay, 2 people need to make a guess. A guess is always better than no answer. Agree? Okay, here we go. How'd we do? Ooh, I hope it's B. Okay, so what are we doing in the reaction? We are doing an addition, right? What's adding? A what and a what? A hydrogen and a bromine. Don't start throwing OHs on there, okay? Just because they're in the peroxide. All right, an H and a bromine. So what are your 2 best choices so far? B and D. Okay, everybody see that's out and that's out. Okay, B and D. And does it add Markovnikov or anti-Markovnikov? Anti-Markovnikov. Now, anti-Markovnikov means who gets what, okay? One gets an H and one gets something else. But anti-addition is adding on opposite sides, okay? So don't let the antis get you mixed up. Okay, so which one is it? B. Because this one has how many hydrogens? 2, and this one has 1. So the one that has the least gets the hydrogen. Okay, so let's say I want to make that compound over there, that 3-bromohexane. Okay, is that on your?
Yeah, it's just a page board.
Oh. Okay, so here's my compound. I'm going to add HBr, and I want you to tell me what compound you're going to use to make it. In other words, go backwards. So your boss says, I want you to make this. You go in, it's your job to go into the lab and make it. by adding HBr to an alkene. Okay, what alkene should you use? Okay, so how are you going to approach the problem? Okay, so here's the bromine. So the carbon the bromine is attached to is obviously going to have to be what? One of the carbons of the double bond. Agree? Okay, so what are basically your options? Where would the H have to get added to? Okay, so we can have CH3, CH, double bond, CH. How many? 1, 2, 3. All right, you see how we came up with that? That's this bromine and one of these hydrogens. Okay, and we made the double bond there. Okay, what's the other option though? Put the double bond on the other side. That'll be the blue route. So we will have CH3, CH2, CH, double bond, CH, CH2, CH3. I scribbled all over this 4 slide. Okay, so which one you think would be the better choice? The first one, why? You like it. It looks better. What?
Doesn't require the.
Do either one of them require the peroxide?
Oh.
No. The peroxide is used if you want to add anti-Markovnikov. How many hydrogens are on this carbon? 1. How many are on this one? 1. So you can't, it's not going to matter if you use the peroxide. You don't need the peroxide. Okay, and it's faster, by the way, just to throw it in there. It adds pretty quick. Okay, what's the difference between the 2 alkenes? Yes, one is symmetrical. Y'all see that? This one is symmetrical. So if you add HBr to this one, remember they both have 1 hydrogen. You're going to get a hydrogen here and a bromine there, but you're going to get the opposite too, bromine there and hydrogen there. Okay, so you're going to get 2 different products that you then have to go to the lab and clean up and separate. If you add HBr to this one, notice you get the same thing no matter which way it adds. Okay, if you put the H on the left or the right and the bromine on the other, you're going to get 3-bromohexane, right? That makes sense. Okay. So those are some of the things to look at when you have to figure out which one to use. Okay, this one, the top red one, gives 2 different products, and the bottom one, the blue one, would only give you 1 product. So it's a whole lot easier to do a simple distillation and distill it over and be done with it than to take that top one and have to separate those 2 into fractional. Okay, maybe multiple times. Okay, makes sense? Okay, are we good at figuring out how to come up with where the double bond is? Where the double bond goes. Okay, notice that the double bond wasn't here. Does everybody see why this one is wrong? You wouldn't even get the bromine on the 3rd carbon. The bromine would want to go to the 2nd. Okay, you would still get only 1 product, but you wouldn't get the right product. Okay, so does that make sense? You see where to figure out where the double bond goes. Start with where the bromine is. You can go that side or that side, okay, to have your double bond. Okay. Okay, how about these? Okay, so what will you get if you do this reaction up here at the top? Do you have this page?
Yep.
Yeah, no, I can see. Look at their pages. I'm like, oh. What do you think you'll get? What's your choice? Okay, so what happens?
Gonna read.
Ah, very good. Okay, because, okay, so what's the first carbocation that you get? Draw the structure of that one. And then decide, oh, I guess I'll put the H there. Okay, what's going to move? Can something move to make it more stable? That one is secondary. So we're working to get to a tertiary. Okay, so what'll migrate? One of those, right? All right, let me get back to here. Okay, so that's your product. What do you think happens on the bottom? Okay. Okay, and I didn't ask you, but how do you know that this one is Markovnikov, the top one? There's no peroxides. That's right. Okay. How about the bottom one? Is this one Markovnikov or anti-Markovnikov? Markovnikov, because it's HCl, it's always Markovnikov. Okay, so what would be the structure of the first carbocation that you would form from this one? Okay, there's your clue. The double bond goes away. Who's going to get the hydrogen? The one on the left or the one on the right? The one on the right, them that has gets Markovnikov's rule. This carbon is going to be plus. Okay, now, does the chloride just add to that or does something else? You want to move the methyl? You could move the methyl, and that would give you tertiary, right? But remember that carbocations have what hybridization? sp2, and what is their geometry? Trigonal planar. So what do you think about that carbon being flat? It's going to be hard because it's in what size ring? 4. Okay, so if this moves and makes the ring larger, see what we get? We get a thing that I wish I could draw up here. We're going to get okay, so instead of being bonded to this carbon down here is now going to be bonded to that one. So what size ring do we have? 1, 2, 3, 4, 5. Did I do it right? No, I lost a carbon. My bad. Okay. I'll fix it. So it'll be right on your stuff. Okay, so here it is. This one is the new bond. The red bond is the new bond. This is the new bond right here. Okay, so what does that look like if you draw it kind of normal? It looks like that. And then this is where your that was exciting. This is where your carbocation is. So chloride adds to that. Okay, it's a whole lot easier for a 5-membered ring or a 6-membered ring to make carbocations than. Okay, now I think I have some in this little box. Oh, this is called a ring expansion. You can have ring contractions where they get smaller too. That would be like a 7 going to a 6. Remember, 6-membered rings were the most stable. And then 5, and everybody will do stuff a lot of times to get to that. Okay. Why is a 6-membered ring the most stable? Because of the what? The chair conformation. The chair conformation. Okay. Remember when we flipped our chair? Literally. Oh my gosh, that was so last semester, huh? I'm telling you, it all comes back to haunt you. How is the review going? Have you gotten on sampling? It was hard, wasn't it?
Yeah.
You had to think. That was the goal, to make you think. I will open chapter 8 is gonna open. I think I already set it up. It's gonna open. Can you see chapter 8? Could you see that it was there but not available yet? Okay, maybe it doesn't. Okay, all right, so now we're going to do some acid-catalyzed addition reactions. So what does acid catalyze? Acid means what? Something with that donates a hydrogen, okay? Catalyzed means that it's regenerated, okay? So you're going to use the H plus and you're going to get it back. So when you do your acid-catalyzed addition mechanism, you should remake that acid somehow, okay? Okay, the first one we're going to do is hydration. So what do you think we're going to add to the double bond? Water. We're going to get hydrated, okay? The acid catalyst that we use is sulfuric acid or phosphoric acid. We do not use HCl or HBr. Guess why? Because what do HCl and HBr do to double bonds? We just did it. They add, right? So you would have halogenated stuff as your byproducts in there, and ugh, it would be a mess. Okay? And FYI, it's Markovnikov. So what is that telling you? The one that has the most hydrogens gets the hydrogen. Okay? Okay, why? Same reason as last time. You're going to make a carbocation, you're going to make a stable. Okay? So here is a generic one. Okay? Which carbon has the most hydrogens? The one with 2 R's or the one with 2 hydrogens? All right, I'm just checking on you. Make sure you're awake. Okay, so that's the one that's going to get the hydrogen, and the other carbon is going to get the OH. The OH is from the water. Okay, when you have sulfuric acid, when you get sulfuric acid, like to use in a lab, okay, it's a solution in water. Okay, phosphoric acid is the same way. When you get these things, remember that the acid and the water make hydronium ion. Okay, so because of that, in your mechanism, you don't have to write out sulfuric acids. With a structure, you can just use H3O+. That's fine by me. Okay, it's pretty fine in your book too. Okay. Okay, so first thing I want you to do, we're going to do the mechanism, but first you're going to predict the major product. So the top one, we got water and H2SO4. What am I going to get? Who gets the hydrogen? The one on the right. And the other one gets the OH. So we make isopropyl alcohol. Little rubbing alcohol. Okay, how about the bottom one? We're going to add water and phosphoric acid. So what are we going to make? Who gets the hydrogen? The bottom one, yes, because it only has how many hydrogens? One, just one. Okay, now, do you notice that I drew those funny arrows? Do you remember what those arrows are? Back from the general tab. Equilibria, okay? That means that this reaction could go either way, okay? Do you remember that we took alcohols last semester and we added acid and we made double bonds, didn't we? You can go either direction. It depends on your conditions. If you add a lot of acid and you heat it up, it goes to the left. If you keep it kind of cold, you know, maybe a little ice bath going, you don't want it too cold, you'll just freeze the water, then it will tend to go to the right. Okay, so this is an equilibrium. You can make it go either way. Okay, also to go forward, we usually use only a small amount of the acid, like 1%, 1 to 10% probably. Okay, it's not going anywhere. Okay, so here's the mechanism. I kind of cheated and stole it out of your book. Well, y'all, it takes a long time to draw them all out. All right, so here's our double bond, and we're adding H3O. So what happens when you add an acid? You protonate. That is always going to be the first thing. Notice that when we added HCl, what do? We protonated the double. We're going to do that here as well. So we're going to have our electrons, our pi bond are going to reach out and pluck off that hydrogen, and they're going to make a bond. Which carbon is going to make a bond to that new hydrogen? The left one or the right one? The right one, because what does the left one then become? Positive, just like we did before. The only difference is the acid's a little different. Okay, so we're still going to make the most stable carbocation. All right, for some reason I have it this way. Okay. All right. Okay, there's our carbocation. Okay, that is still our rate determining step. We haven't drawn one of those yet. We'll get to those. All right, and then we have water that we formed. There also is water in there. You can't get away from it. There's water in there. So the electrons on the oxygen are going to go to the carbocation. Okay. What does that give us? That gives us our alcohol that is protonated. And then what do we have to do? Deprotonate. Now, notice that what we didn't do. We didn't add OH minus, right? Hydroxide ion, because there isn't any in there. Okay? So if you went through general chem and analytical and got beaten into you that water and water makes H3O plus and OH minus. Okay, that's like so small. Okay, it's like inconsequential. Okay? When you have acid in a solution, you're going to have positive things and neutral things when it comes to water. Okay? You're not going to have OH minus. If you want OH minus, you're going to put sodium hydroxide in there. Okay? So notice that water is what adds. The most common mistake I see is people will take the double bond and attach and go to H2O and lose OH minus. First of all, water does not protonate, acids protonate. If you didn't have the acid in there, if all you had was the double bond and you threw water in there, you know what would happen? Nothing. Your alkene would get wet. That was it. That's it. You'd be all wet. But you wouldn't get addition to the double bond. You've got to have the acid. All right, so here's our little acid. Okay, and now we're going to deprotonate it with water. Water can act as a base when you have a really strong acid in this, like something that's plus. Okay, the O plus, the H3O plus, the H2SO4, whatever acid you threw in there to begin with. So the water will pull off that, and you'll get your alcohol plus your acid. So your acid is regenerated. What can that do? It can go protonate another one. Okay? All right, got it? It's not too bad. It's the same as the HCl HBr mechanism. The only difference is you have this extra step here because you don't have minus to plus. Okay? Because you have neutral to plus, so you have to deprotonate. Okay? All right, what if we change out the water? How are we doing? 11:45. Okay. We change out the water and we add an alcohol instead. Typically, this gets done with small alcohols like methanol and ethanol, but I've seen some people do some wacky things with some bigger ones. But this is analogous to hydration. Okay, you still have to have your acid catalyst, but your product is going to be an ether now. Remember what an ether is? ROR. Okay, so instead of having ROH, you're going to have whatever that alkyl group is on your molecule. All right, so here is our alkene. Okay, we're adding an alcohol with an acid. Okay, it's still analogous to hydration, so it's still Markovnikov. You're still going to protonate. First, you're still going to go through a carbocation. All of that is the same. All that we are changing is that one of the hydrogens of the water has been replaced with an R. Okay, so what is your product going to be for a generic? And you could even make this R prime so that it looks like a different R. It doesn't have to be the same. Someone will come up with that later. They'll go, wait, why was it the same? Okay, so instead of the OH, you're going to have OR. Okay, and if you put the little that way, it's a prime. It's a little too jobby. Okay, all right, hang on. Let's look at this. Maybe. Okay, so what do you think the organic product is from that one? Almost the same as the one that we did before, except instead of having H2O, we have methanol. So what do you think we will get? Well, be that way. Doesn't want to go away. Okay. See how we got it? So what do you think happens in the mechanism? When you take that alcohol and you add H2SO4 to it, you're going to get, don't forget, there's two lone pairs on the O. And this is equilibrium. You're going to get, I'm not really worried about that equilibrium thing, but you'll see it. You're going to get that plus HSO4 minus. That's HSO4 minus. Can you read that? Maybe I can fix it. I've got 2 minutes. All right, so that's what's going to function as your acid now, is the protonated alcohol. Okay. Typically, you put that stuff together and then you add the alkene. Is how you do it. So there's no question. Remember, protonation is fast, fast, fast. Okay. So now we're going to protonate our double bond and make our carbocation, and then the alcohol adds. And then look what we have to do. We have to deprotonate, exactly like the last one, except the alcohol is doing all the work. Is there water in there? There is some water in there. But what you would do is you try to overrun it by using a lot of alcohol so that the chances of the water adding are going to be really small. Okay, that's kind of how you do it. All right, I'm going to fix that so that it looks right. Okay, so hopefully you will have a video posted today. Barring any more complications. There. Does that look a little better? That way when I print out the slides later, they'll look better. Okay? Go practice. Get your review done. I'm going to go eat too. That sounds
I was
good.
going to ask
Let's
you
go
about
eat.
the homework. If you get it wrong, there's not an option anymore that shows you.
Well, it should be
You
there.
just have to keep getting it wrong, and they're show you like the give up option to get the answer. It's not
I'll go look.
Okay.
And see if something weird happens. Okay, that's odd though.
We were like, yeah.
Yeah, yeah. Oh, thank you, Lindsay. All right, so I click end the meeting.